yeah, hill climbing, yeah, and yeah, this part, yeah, hill climbing, yeah, and also simulated annealing, local beam search. Right. So then also I have introduced this part, yeah, about the genetic algorithms. Okay, GA, genetic algorithm. So today we are going to learn, yeah, study about this part. Yeah, so genetic algorithm, GA, yeah, I mentioned also some part of this slide, yeah. So it is a search technique that is a variant of actually the stochastic beam search. And then it is inspired by the biological evolution process and uses the concept of natural selection and genetic inheritance. Yeah, and it was developed by John Holland in 1975. Right, so then as we can see here, as an individual is usually represented by the strings. Yeah. This is the important things, yeah, zeros, yeah, and ones, yeah, or digit. And the objective of function is called a fitness function, yeah, and usually it starts with k randomly generated states. So these are the concepts, yeah, from the biology about the genotype and in genetic algorithm and genotype in biological system. So actually it is inspired by the genotype, yeah, and phenotype from a biological system. And these are the terminologies, yeah, taken from the concept of the biology, yeah, like genotype, type, crossover, mutation, fitness, and natural selection. So these terminologies we use in genetic algorithms, yeah. So then we have the crossover, mutation, fitness, and as well as the natural selection. And this is the general scheme of evolutionary algorithms, yeah, as you can see here. So start from initialization, yeah, it's actually randomized, and then population, yeah, this is the population, and then the parent selection, yeah, parent and recombination, yeah, and after recombination, the mutation, yeah, and there is offspring here and survivor selection and back to the population, right? So if it is not survived and will be terminated, yeah, if survived, then again will go to this cycle, yeah, the process, and it will go to the next process and the next cycle, right? So some here we can say individual may be terminated, yeah, due to and they cannot survive, yeah, in the population, yeah. Then if they survive, then we'll continue again with the next cycle. All right, so this is the basic of genetic algorithms, yeah. So an example here, we want to find the maximum of function here, yeah, fx equal to minus x power 2 over 10 plus 3x, yeah. This is one example, yeah. The function, we have this function, yeah, for integer x element of 0, yeah, comma 31. So assuming we don't know the analytical solution for this. So how about the step, yeah, to find this solution, yeah. So by using the genetic algorithm or basic genetic algorithm, so we encode the parameters as a binary string, yeah. Example here, 5 bits are needed, yeah. This is an example, yeah. So we put the 5 bits, yeah. So this is 5 bits, 1, 2, 3, 4, 5, yeah. And then we set up an initial population of random strings, yeah, such as this 1, 0, yeah, or 10, yeah, yeah, and chromosome number, we can say it's on. Yeah, so we set up the chromosome number, yeah, the population, yeah, of random string from 1 to 10. Yeah, so start, yeah, from 1 until 10. Yeah, for example, this is the initial population. Yeah, so given this data are given, yeah, as the basic of the population, yeah, for the initial population as the base. Yeah, we use this kind of data, yeah, and then we have this function, yeah, and the binary string, yeah, with the initial population of random strings. And then the third step, yeah, step number 3, yeah, compute the fitness of each chromosome. Yeah, as we know that given this chromosome number, yeah, and initial population, yeah, right. So we bring this one when we create another table, yeah, here for the step 3, yeah, compute the fitness of each chromosome. Yeah, this step 3. So this you can say step 1, step 2, 3, compute the fitness of each chromosome. And we have a chromosome number and also initial population, yeah, are given already on the data from the previous step, right? So from number 1, yeah, until number 10, yeah. So these are the initial population with the binary, yeah, binary string, and this is the random string here. Yeah, and then the X value, yeah, this is the X value. So since the initial population is in binary, so we have to convert to be the decimal here, yeah, for value. Right. So this one, yeah, if you remember the binary conversion, you should convert this one. Yeah. So start from the right bit here. Yeah, there is a 5 bit, right? 1, 2, 3, 4, 5. So 1, 2, yeah, 3, 4, 5. Right? So we count this binary, convert to be the decimal, yeah, in order to get this value. Right? So this 11, yeah, from where 11, we just provide this one. Yeah, 1 times binary, yeah, 2 power 0. And this is the second one, 1 times 2 power 1. 1 times, 0. The third one here is 0 times 2 power 2. Yeah. And this is the fourth. Yeah. 1 times 2 power 3. Yeah. And this is the last one, 0 times 2 power 4. So this one, the first one, how much this one? We get 1 times 1, right? So equal to 1. This is 1 times 2 power 1 is 2, right? So equal to 2. And this is 0. Yeah. 0 times 2 power 2 is 0 and 1. Yeah, 2 power 3, 8, right? And this is 0 times 2 power 4, so 0. So we get 11. Okay, understand? So until this part. So because you have to find these all values, yeah, from the binary value here from initial population. Then you have to calculate the binary, yeah, X value. Yeah. So for example, this one, number 9, this is 3. Yeah. So because of only this first bit, the second bit, they have 1, yeah, 1 number. So means that 1 plus 3 only. The others, yeah, the remaining bits are 0. So 1 plus 2 is 3. So this is 3. Yeah. This one 9 because of 1 plus 8. Yeah. Only this one and this one. Right. So then you count this one. Yeah. And you get these numbers, all these values. Yeah. This is 2. Yeah. The second one. 1 times 2 power 1. So equal to 1 times 2. Yeah. So equal to 2. Yeah. So you count, yeah, all this value from the initial population, yeah, from the binary, then you will get this value. 11, 26, 2, yeah, 14, yeah, here, and 12. You have to count one by one, yeah, all 30, 22, 9, 3, and 17. Right? So we have the formula of fx. Yeah, we can say this one as a fitness value. So then the fitness value here, yeah, you can see here. This is, we can say this one as a fitness value. Yeah, fx. Yeah, this one fx equal to, yeah, minus x power 2 over 10 plus 3x. Right? So this is the fitness value here. Yeah, given this formula is given. Yeah. So then the fitness value. Right. So then you just key in, yeah, all this value, yeah, according to the chromosome number. Yeah, for example, this one 11. 11, yeah. So you just put this one F11 equal to minus, yeah, 11 power 2, yeah, over 10 plus 3 times 3 times what's it 11. Can you count this one? This. So just we need to confirm that the result is the same. Yeah. The result is 11 power 2 is 1 to 1, right? So minus, so we have to power this one, this number for us. So 1 to 1 minus 1 to 1 over 10 plus 33, all right? Yeah. Okay, so then equal to, since this number is divided by 10, so minus 12.1, right? Plus 33. So equal to this one, yeah, 20.9, right? Okay, so then you continue, you proceed all this value, this one, yeah, X value, and this is the first one, yeah, for the chromosome number 1 with the initial population, this one, this binary, and you will get the value of X here. Yeah, so you just count the decimal of this population, this binary number, and you will get the value, yeah. And then the value you enter the value here, yeah, to the fitness value given, yeah, usually given, yeah, here in the case, yeah, in the problem here. So then that you in one by one, yeah, enter the number here, the value, yeah. So then if you put 11 to this fitness value, then you will get 20.9. So can you check this one, please? One by one, using the same step like this, then just want to confirm and to be familiar with this calculation. Yeah, so with the 11, you will get the 20.9. And what happened with 26, with 2, with 14, with 12, with 30, with 22, with 9, with 3, and with 17. 3, yeah. F3, we put 3 here. So F3 equal to equal to sorry, uh, 3. Oh, I don't know why it always appear like this. Yeah, minus here. Over 10 times, yeah, 3 times 3. Right, because of the next 3 is, I mean, X is 3 here. So this one, yeah, 9, yeah, minus 9 minus 9 divided by 10 plus 9. So minus 0.9 plus 10. So equal to 8.1. This one. So you can check all this number, yeah, in order to confirm the result, yeah, whether the result is the same or not. This one, yeah, 30, you will get a 0. Yeah, with 30, yeah, here the result is 0. Get the, yeah, from this result you sum of this result, yeah, here, and you will get a 147.6, and you make it average, yeah. So divided by 10, because of the number of the chromosome is 10, so we will get the 14.76. And then from this part, yeah, the maximum value, yeah, for the fitness value is 22.1. Okay, please try to find this, yeah, one by one. Yeah, maximum value. Yeah, that I will come back to explain again for the selection probability. Same result? Okay, good. All right. So then we continue with the selection probability, yeah, from this fitness value, yeah, we got the summation of this fitness value, yeah, which is you just add these all fitness values, and you will get the 147.6, yeah, here. And then the average, yeah, you just divided this summation with the average, yeah, I mean with the chromosome number here, 10. So then you will get the 14.76. And maximum value, fitness value, you're just looking for the maximum value from this fitness value. Then you will get the 22.1. Sorry, 22.4 here. Here is, this is the highest, yeah, the maximum, and not 22.1, but 22.4. Yeah. So this fitness value is the highest among this population, among this number, yeah, all right. Then for the selection probability, you divide this number, yeah, for each individual here. Yeah, for example, the first one, yeah, 20, yeah, this one. So we'll remove this probability, yeah, actually from 20.9 divided by the summation here, the total, yeah. So you will get the result, yeah, 147.6, yeah. Right, so please count this one, 20.9 divided by 147.6. Okay, so you will get this number, right? 0.14, we round to be 1.6. Yeah, actually 1.59 something. Right? So you count this one by one by one, please. So make sure that you will get the same result. You get the same result like this. So the second one, 10.4, yeah, divided by 147.6. Right, so then you will get 0.0705. Okay, please check the others. You will get all this part, yeah, selection probability. So for the third chromosome, you will get the 0.0379, yeah. And then fourth, you will get the 0.1518, yeah, 0.1192, yeah, 0.1280, 0.0549, and 0.1497. Yeah, after you got this all, the selection probability, then you move to step 4. Select the chromosomes that will reproduce based on their fitness value. Yeah. So then the probability of selecting X, yeah, is Fxi, yeah, over sigma, yeah, Fxk. Yeah. So then the generate a new population using crossover and mutation based on the selected individuals. Yeah. So then we select which one, then the total, I mean the the individual, yeah, divided by sigma of the, yeah, for the probability, this one, yeah. This is the formula, right? The formula, this one, yeah, of the probability divided by fx, yeah, equal to fx divided by xi, yeah, right, by sigma fxk. And k is actually the total, yeah. Formula of this, yeah, for the selection probability is a fitness value given. So after the fourth step, we got the selection probability, and we continue with generate a new population using crossover and mutation based on the selected individuals. Yeah, so this is the selection. Just for the example, yeah. In this case, we give the selection by using the rolled wheel selection. Yeah, then for the selection of the individuals for reproduction. Yeah. So each member of the population allocate the space on the roulette wheel in proportion to fitness. Yeah. So we know the fitness. Yeah. And the fitness, the percentage like this. For example, this is 14.16. So then we allocate, yeah, accordingly. Yeah, the probability. If we use the this one, use almost the roulette wheel selection. So you put this one, yeah, this is just for example, yeah. This is not representing the previous one. So, number one, yeah, the the probability, selection probability, yeah, here. So 14, for example, and number two, 49. So you just allocate accordingly here. Yeah. So if you have 10 members, yeah. So then you have to provide divided 10, yeah, by 10. This was it, the roulette wheel, yeah, this circle, yeah, you have to divide, yeah, 10 because we have 10 members, yeah, for this case. Yeah, so in this example we put only 4, yeah? Because this is just the example. Then you can draw, yeah, the roulette wheel, yeah, of this selection, yeah, for this case, yeah, with the 10 members, right? So then allocate accordingly. Yeah, for example, the chromosome number 1, this is 14.16%. Yeah, that's probability. And you times with 100%, and this is 7%. Yeah, and the third member is 3%, and the fourth is 15%. Yeah, right. And 6, nothing, 0. And from this, which one the highest, the percentage from this part, from this chromosome? Yeah, there is 10 members here. Which one the highest probability here? Number, now what the number, yeah, of the member here, the highest probability?
Number 4.
Number 4, yes, exactly. So number 4 is the highest probability. Yeah, in terms of the selection probability. So means that here you just allocate, yeah, this number accordingly, yeah, according to this circle, right? And spin the wheel and put individual where it stops into the mating pool. Yeah, this is a tentative new population, and repeat until the mating pool is full. Yeah, you just rotate this one. Yeah, I mean rotate this one, and then it stop in which, yeah, which number, yeah, then you put at the mating pool, yeah, this number, and repeat until the mating pool is full. Yeah, so the strategy ensure that the fittest individuals are more likely to be selected for reproduction, yeah, based on the roulette wheel selection. Right. And then for the crossover, the process of crossover, randomly select the parent 1 and parent 2 from the mating pool. Yeah, then we got from this selection. Yeah, and then without the replacement. So randomly select crossover point K, for example, and swap genetic material. Yeah, for example, here we give even the parent, yeah, from the mating pool, yeah, got this number, yeah, and then we swap this genetic material, yeah, from the parent 1 and parent 2, yeah. So swap here, yeah, only this part, yeah. Only this part, sorry. Yeah, swap. Right. So then, yeah, from the swap genetic material, we get the children here. Yeah, so first one is 0, 0, 0 all. Second one is 1, 1, 1 all. And then after we swap, yeah, the genetic material, then we get this number. Yeah, 0, 0, 0 because of 1. Yeah, swap to the top, yeah, above, yeah, the parents 1, we say is the parent 2. Yeah. So then we got this number. Yeah, 0, 0, 0 with 1, 1, 1 and 1, 1, 1 with 0, 0. So this is an example of single point crossover, right? So, and for multi-point, yeah, we have a different case here. So for a long chromosome, use several KS, yeah, for multi-point crossover. This is a parent 1, for example, parent 2, yeah. So this is a children 1, yeah, child 1, child 2, yeah. And then, yeah, we put, for example, here, yeah, with the multi-point, yeah, not only single point, yeah. Previously we divided, yeah, here this part and crossover, yeah, and swap with the counterpart here and the P2, and we got the children, yeah. And for this multi-point crossover, yeah, so we divide it into some part, yeah, that we will swap this part. Yeah, for example, this is, we can say the first part, yeah. Yeah, and then this is the second part. Yeah. So we divide it into 4 parts. Yeah, the first part we do not swap. Yeah, the second part we swap. The third part we don't swap, and the fourth part we swap. So then we swap only in this part and also in this part. Yeah, only that part. So it called as the multi-point crossover. Yeah, then based on these swaps, so then we get this number. Yeah, so 1, 1, 1 move to top. Yeah, and this is maintain the same, and the last one, and the number 4, I mean the fourth part here, swap, yeah, 1 to top and 0 to down. So we get the crossover for multi-point. All right, so we finish the selection and also crossover. Yeah, and the mutation. So the process of mutation, yeah, we apply the mutation operator to the children, yeah, to the children. So we get the children. After that, we apply the mutation and select and flip some bits, yeah, with very low probability, yeah, we can say, or with low probability. So if probability is set to high, such will turn into a primitive random search and place children in the next generation. Yeah, so this is the mutation. And mutation preserves and introduces diversity and prevents getting stuck in a case where all population are very similar or exactly the same. This is an example of crossover point. Yeah, is 2, yeah, in this case. And then mutation point is 4. Right, so parents, yeah. Here, so we have this one, yeah, parent 1, parent 2. So crossover point 1 and 2, yeah, 2 here. And then for the mutation point, yeah, we select 4. Yeah, 4. Then child number 2, yeah. Yeah. So select as the mutation point. Yeah, so child number 2 has been changed by mutation operator. Yeah, because of supposed to be 0, 0, 1, 1, 1. Yeah, according to the crossover, this one. Yeah, yeah, crossover. Yeah, so based on the crossover, this crossover, then we select child 2. Yeah, number 4, point number 4 here. Yeah, with mutate with the 0. Yeah, and we'll get this mutation. All right, so since our population has 10 chromosomes and each mating produces 2 offsprings, yeah, so we need 5 mating to produce a new generation of 10 chromosomes, right? So then these are 2 matings, yeah. So then we get this new population, yeah, based on the previous chromosome number, yeah, and mating pairs and the population and value and the fitness. Yeah, so then from the fitness value, yeah, we got the summation and average, yeah, and the maximum. All right, so that is the example of GA. For example, we have another example for the case. Yeah, we apply on the case study. Yeah, for the next slide. Yeah, for the second part of this lesson. All right. So then the next one is the 8 queens problem. Yeah, representation is another example. Yeah, for phenotype, yeah, port configuration is this part, and genotype, yeah, for mutation of the numbers 1 to 8. Right. So there is a number 1 to 8. Yeah, the port is 1, 1, 2, 3, 4, 5, 6, 7, 8. Right. So with the permutation, so we'll get this one, for example. Yeah, so we change, yeah, mutate some location, yeah, for number 2 to number 3, yeah, and number 4, yeah, number 2 change with 3, and number 4 change with 2, yeah, and you can see here 5 also change, yeah, 6. So then this is the permutation, yeah, from the previous set configuration. And penalty of 1 queen, yeah, the number of queens you can check, and the penalty of your configuration, the sum of the penalties of all queens, and notes that the penalty is to be minimized. Yeah, fitness of the configuration, inverse penalty to be maximized. That is the fitness evaluation of the 8 queens problem. So we have to make sure that there is no against, yeah, for each queens in this case. And this is the original port configuration. Yeah, so then you have to perform some movement, yeah, in order to make the goal, yeah, how to reach the goal. And so the Queen's problem, yeah, for the crossover, combining 2 permutation into 2 new permutation, yeah, using cut and crossfield crossover, yeah. So then we choose the random crossover point, yeah, and then copy first part into children, yeah, and then create the second part by inserting values from the other parents, in order to appear there. So this is the original one. So then we create this part. We put this first part. Copy the first part. So it will be the same. First part. This is the crossover. Similar with the previous example. And then we change. Change the the second part. So for the second, create the second part by inserting values from other part. This is in the order they appear there, and beginning after the crossover point. Crossover point here, and skipping values already in child. So otherwise we'll get the redundant numbers and not really a permutation. Right. So then you have to make sure that there is no the same number on the same line here. So then if there is a same number, means that it's not really a permutation. Right. So then as you can see here, there is no same number. Even though we perform the permutation, also we have to consider the number. So the crossover should be for the different number. Right, so then this is for the mutation. Small variation in one permutation. Swapping values of two randomly chosen the position here. So randomly chosen the position. Number 3. And number 7. Here. This is number 3. This is number 7. And you swap this. This number. Then you will get this one. This randomly selection. And otherwise, if mutation is applied to only one position, it will cause a redundant number to appear. And if redundant number, then it is not really a permutation. And then the selection, selection and population, update can be done in multiple ways. A simple scheme could be the parent selection. Pick 5 parents at random from current population and take the best to perform the crossover. So this is the parent selection. And for the survivor selection or replacement, so you insert a new child into the population and choose an existing member to replace. By using this method, sorting the whole population and decreasing the fitness, or enumerating this list from high to low, or replacing the first with a fitness lower than the given child. So we have a fitness value, right? So then we can check from the fitness value, the lower one, from the first, from the previous. And then we replace the number. So this is the summary with the queens, 8 queens problem. So the presentation with the permutation, combination, the combination probability, the mutation probability 80%, combination probability, recombination probability 100%. Parent selection, best 2 out of random 5. Survivor selection, replace the worst. Population size 100, sample number of string 2, random, and 10,000 fitness evaluation. Then this only one possible set of choices, operators, and parameters. And if you want to learn more about this GA example, so you can study also from the TSP, traveling salesman problem. In this link. So the goal is to find the shortest tour between n different cities. So we have a n number different cities, and testing every possibility for an n city tour would be n. And different cities, and city tour would be n, and a 30 city tour would have to measure the total distance of this one, 2.65 times 10 power 32 different towers here. And assuming a trillion edition per second, this would take this year. Yeah. Assuming a trillion edition per second, right? So we'll get these numbers, so very big numbers. And the solution you can see from here actually. If you want to see, just click this, and you will go to the website if you want to see more about the TSP salesman, traveling salesman problem for the GA example. And one version of GA, the function genetic algorithm, with the population, fitness, FN, returns, and individual. So this function and input, the population, and the set of individuals with the fitness FN, function that measures the fitness of an individual. So the population given, set of individual, like the previous example, we have 10 individuals, and then the fitness function also given, and then you use the formula to find the selection probability, from the fitness function, for the number result from the fitness function, and repeat, the new population, empty set, and for I equal to 1 to size of the population, do X random selection for the population with the fitness function, Y random selection population with the fitness function. We'll get the child, reproduce the child, and with X, Y here. And then if small random probability, then child mutate. If small random probability, child mutate. Add child to new population. We'll get the new population until some individual is fit enough or enough time has elapsed, and return the best individual in population, according to, again, to the fitness function. All right, so when to stop this process? When to stop the evaluation process? So we could stop after some number of generation, or fitness function evaluation, and we could stop when the best solution found, and has not changed for several generations, the same best solution, and stop when average fitness of the population doesn't change much between generation. So average, we get average fitness, right? With average fitness, actually the total summation of the fitness, fitness value, after that divided by the number of the individuals, and we'll get the average fitness. And average fitness of the population doesn't change much between generations, so we can stop the evolution process, and stop when convergence is achieved. So a gene has converged when 90% of the population have same value, and the population has converged when all the genes have converged. Right. Can you see the slide? Okay, so right, so these are the condition when we stop the evaluation process, and then the building block the hypothesis. So why do genetic algorithms works? So actually it is a very little theory, only some intuition, and building block hypothesis is then proposed based on the this consideration. Individuals contain some fragments, or building blocks which are good and some which are bad. That is the condition, or the building block hypothesis. And then the crossover results in exchange of building blocks between the individuals. That is the condition of the crossover. So as we saw before, so there will be an exchange between the block for the individuals. And then the new children which are lucky enough to get the good building blocks from the parents will have a higher fitness. That is the hypothesis for the building block. Right? And then GA is actually the evolutionary computation, and it is using the following step, encode the problem parameters as a fixed length binary strings, as I shown you before. I have shown you in the example, and then fix a fitness function. So then we have a population with a number of individuals, and we have a value for the x based on the binary. So we have a decimal, and after that we have a fixed fitness function. So fixed length binary string, fixed fitness function, and use predefined operators for binary strings for the selection, crossover, and mutation. So these are the steps in the GA and evolutionary computation. And we no longer restrict ourselves to fix the length chromosomes, binary encodings, and operator. So we get a different kind of evolutionary computation. And in genetic programming is one member of evolutionary computation family. And sometimes this considered as a kind of variation of the genetic algorithms. So this is the genetic programming, it's actually variation of GA. That each variable length chromosome encode the program. For example, LISP, LISP, and let the fitness LISP, and let the fitness function be an execution of the program. Then it will generate the output that can be ranked. So then we can arrange based on the rank, and let crossover generate this syntactically correct programs. And then let mutation be a random rearrangement of statement. So if you want to see the example, teamwork in genetic programming, then you can access this link. So you can access this link, genetic program that will evolve the solution programs emulating the food collection behaviors of ant. All right, so the summary, the population of individual exists in an environment with limited resources, and the competition for those resources causes selection of those fitter individuals that are better adapted to the environment. So individuals act, the seed, or the generation of new individuals through the recombination and mutation, with the crossover and mutation. And the new individuals have their fitness evaluated and compete, actually for the purpose of those survival. And over time, natural selection causes a rise in the fitness of the population. And this is the characteristic of evolutionary algorithms, stochastic, and it is population-based algorithm. And in terms of the recombination and mutation, create the necessary diversity and facilitate the novelty. And the selection reduces the diversity and acts as force pushing the quality. So this is the selection. This is the, especially recombination, crossover and mutation. Right, so then this one you can test during the, check during the tutorial then. Okay, we check this part. This for the example. Web here.
Yes, sir.
Okay, good. So traveling salesman problem using GA, genetic algorithms. So this is the case. We have this case, run the traveling salesman problem simulator. Develop solution to the traveling salesman problem using GA. And the goal is to find the shortest distance between n different cities, and the path that the salesman takes is called a tour. So then you can explore this one, study, to see and check the application. Example of the genetic algorithm in TSP. So two complex issues with GA to solve TSP are the encoding, the tour, and the crossover algorithm that is used to combine the two parents' tours to make the child tours. So in the standard GA, the encoding is simple sequence of numbers, and crossover is performed by picking a random point in the parent sequence. As I have shown before. So then we want to crossover, to make a crossover. So then we pick some random point as the parent sequence, and switching every number in the sequence after that point. So then we put, for example, this one, the parent. So put it 3 parts. The remaining we perform the crossover. Right. So as you can see here, parent 1, parent 2. Parent 1 with FAP, ECGD. Parent 2 with DA, CGBF. And the child 1, actually the crossover, or so we picking the random point. For example, this is the 4 remaining digit or point, ECGD, point number 4, 5, 6, 7, and exchange with the parent 2, parent 1, parent 2. So then we'll get the first child, FAP with CGBF, with this one, right? FAP with CGBF, and DA, the child, another possibility, with the DA, ECGD, ECGD with DA. So we make a crossover, and so ECGD with DA and FAP with CGBF. So the difficulty with the traveling TSP, traveling salesman problem, is that every city can only be used once in a tour. If letters in the above some represented cities, then this child tour created by this crossover operation would be invalid. So if it is represented cities and more than one, so then it will be invalid. So the one city can be represented only with one letter here. All right, so then the solution, stores the link in both directions for each tour here, and the above. For example, parent one would be stored as is the CTA. Yeah. So only one city represent one. Only one letter represent one city. So first connection from A to F, and second connection to B, A, E, and then make a. So these are the parameters for the operation of GA. Yeah, and there are 6 parameters to control the operation of GA: the population size, group size, mutation, yeah, maximum generation, random seed, city list. These are the result, yeah, parametric values. So the population size, this one, group size, mutation, nearby cities, and nearby city odds. So these are the program you download, and you can try. Yeah, this is the source code. Yeah, and this, if you want to solve by simulation online, then you can also access this part. All right. And then okay, so this one is genetic programming. Yeah. So can you see the slide here?
Yes, sir.
Okay, so in genetic programming, you can access this part. Yeah, I send you the. So, and food collection, yeah, genetic program, as it is a variant of the genetic algorithm actually. So genetic program that will evolve the programs that will emulate the food collection behavior of ant. Yeah, so this one, yeah, background, what this project is all about, user guides, and you can read all this thing. And the simulation, even you can download the source code, yeah, for this genetic program. Then you can try to run, yeah, and execute. So run is the run of the simulators, yeah. So run the N food collection simulators, yeah. Right. So then you can try to download executable source code here. The case of the cells and profit, yeah, sales and profit problems. And because of the application, we have actually many application of the genetic algorithms, yeah, GA. So to solve the problem. Okay. Right. So this part already mentioned, yeah, evolutionary computation is actually based on computational models of natural selection and genetic. Yeah, and then is an umbrella term that combines the genetic algorithm, evolutionary strategies, and genetic programming. Yeah, and then the natural evolution, yeah, actually the neo-Darwinian paradigm, yeah, process of reproduction, mutation, competition, and selection. And the power to reproduce appears to be an essential property of life. Yeah, so we can say it's the natural evolution. Yeah, and the power to reproduce, yeah, to be an essential property of life, and the power to mutate, yeah, is also guaranteed in any living organism, yeah, reproduce itself in continuously changing environment. And the process of competition and selection normally take place in natural world. Yeah, as we can see, expanding the population of different species are limited by a finite space. And as we can see that evolution can be seen as a process leading to the maintenance of population actually. So actually it relates to the ability to survive and reproduce, yeah, in specific environment. And it's called by the evolutionary fitness. Yeah, and in evolutionary fitness can also be viewed as a measure of organism ability, actually an ability to anticipate change in its environment. And the better organism fitness to the environment, the better its chance to survive. So then the fitness value is actually one of the parameter to see, yeah, to survive to the survival of an organism. Yeah, an organism, this one, yeah, we can say as the fitness value is the survival factor, yeah, or individual, we can say, or organism. And this is mentioned also, yeah, the genetic algorithm, class of probabilistic optimization, yeah, and GA is guided search algorithm, yeah. So this is the important keyword, yeah. So it is the guided search algorithm based on evolutionary process. So GA is still under the search algorithm, yeah, but it is guided. Sometimes we can say is the stochastic, and it is a class of the probabilistic optimization algorithms. So this is the class of the search techniques. Yeah, yeah, we learn about the search techniques. Yeah, so there is a calculus-based technique, yeah, divided into 3 classes in search techniques: calculus-based techniques and guided random search technique and enumerative techniques. Yeah, in calculus-based technique, there is a Fibonacci, and also sort. Yeah, and then in guided random, yeah, guided random search technique, there is a taboo search, hill climbing, simulated annealing, and evolutionary algorithm. So this one, yeah, local search, or in this part, yeah, we learn hill climbing, simulated annealing, and evolutionary. Yeah, these 3. So we don't learn this one. Yeah, so we cover only hill climbing, simulated annealing, and evolutionary algorithm. So we just divided into genetic programming and genetic algorithms. Yeah. Right, and in enumerative techniques, there is a DFS, yeah, depth first search, and dynamic programming, and also breadth first search, BFS. So these are the classes of search technique. Yeah. So we have done study about the DFS, yeah, BFS, hill climbing, simulated annealing, and now evolutionary algorithm. Yeah. So this part, this part, this part, this part, and now here on this part. Yeah, genetic algorithm. And so these are the coverage our course, our module here. So because of not all such technique we covered, yeah, we covered only the some techniques that the most popular, we can say, yeah. Then many application we can see, and many problem can be solved by using this such techniques. All right. Then evolutionary process, yeah, as we can see here to illustrate, yeah, the father and mother, parents, yeah, as parents, and child, yeah. So example of evolutionary process. So I'm going to illustrate the evolutionary process, yeah, by showing the example. This as an example, mice and cats. So basically, it is about the survival, yeah, of the fetus. So that's why it mentioned about the fitness percent probability, the percentage. Yeah, so the percentage of the fitness. So this is the illustration of evolutionary process, yeah, for mice and cat. So in order to survive, we put mice and cat, yeah, on the same place, for example. So mice escape from the cat and cats catch the mice. Yeah, so this is the situation. We put on the same location, yeah, same place, for example, mice and cats. So then in order to survive, yeah, mice escape. Yeah. Mice have to escape, yeah, from that location, yeah, from that place. Yeah, yeah, because of cats, yeah, will catch the mice. Yeah, that is a problem for mice actually. So that's why mice have to escape. Uh, so then how to survive? So both, yeah, find this solution, yeah, how to survive, yeah, in this situation, because of cat also has to catch the mice, yeah, in order to survive. Yeah, and then how to survive here? So they have a different way to survive, right? So, for example, here mice, yeah, in order to escape, yeah, from the place, yeah, from the place here, for example. So mice have to run, yeah, faster. Yeah, that is the first thing, yeah, sample. Then, yeah, how about the cats? Cats is, of course, cats have to cats have to follow, yeah, the mice. Yeah, if the mice run faster, then cats must run faster as well. Yeah, so that is the first one. And then the second one, yeah, the second after run faster, then mice have to, you know, perform or run with the zigzag patterns. Yeah. So otherwise, if you're using the straight line, then we will be, cats will be easily to catch to grab the mice. Yeah. So that is a thing. So that's why, yeah, the mice should run with the zigzag pattern. Yeah. And then how about the cats? Yeah, cats, yeah, from the experience. So the cats also have to understand the pattern. Yeah. So the pattern of the movement, the mice movement, right? So then understand the pattern from the cats. And then from the mice side, then utilize surrounding. Yeah. So mice have to utilize the surrounding, yeah, the environment. And cats, yeah, beware of surrounding. Yeah. So that is interaction actually. So also the action, yeah, after give the reaction, yeah, then can give different action. So these are the way to survive. Yeah, so they have a different way to survive. Yeah, according to the condition and situation. Yeah, that is an evolutionary process. And If we construct the mice and cats algorithm, yeah, based on the previous pattern here, yeah, activities, yeah, or processes. So the mice and cats want to survive. That is one, the objective. And while the mice dead or cats dead, yeah. So then if speed mice more than speed cats, then mice will survive. Yeah. Yeah. Else cats survive. Yeah. So then that is the thing. So the first speed, yeah, if speed of mice, yeah, um, more than speed of cats, then of course the mice will survive. Yeah, is the first condition. And the second, yeah, second condition, if pattern mice more than pattern cats, then mice survive. Yeah, else cats survive. And this one all, yeah, else if not meet the condition, then else, yeah, cats will survive. In this case also the same. And the third condition, if surrounding mice more than surrounding cats, then mice survive. Again, else cats survive. So that is the three conditions, yeah, for this illustration. So end of while, yeah, finish. So until, because so actually they continue, yeah. If it doesn't work with this step, then we'll continue with the other step. Yeah, in order to survive, the main objective is to survive in this case, in this situation. Cats also the same. Cats have to survive. Yeah. So then cats will find the solution also. So based on this, then which one will survive? Yeah. So of course, some of individuals will not survive, but some others will survive. Yeah, that is the common in an evolutionary process. Right. And this is the general evolutionary process. Yeah, as you can see here. Here, the population, right? Yeah, from the population, yeah, there is an individual, yeah, of course. Some individuals and construct a population. The population consists of many individuals, right? So then there is an environment. So then the population actually, yeah, of course, inside the environment, we can say. Yeah, so then surrounding by the environment. And then they have to know and understand the environment and the situation here. All right, so then if the environment, if the population, yeah, here, the respond to the environment strong and intelligent, then it will survive. Yeah, strong, that means that only the strong individuals, yeah, and intelligent, they can survive, yeah, according to the environment, yeah, situation, of course, and then survive and evolve, yeah, and will evolve, then will generate, yeah, the new, yeah, generation, and will result the new generation. And then if the individual is weak, yeah, so then die, end of evolution. So it means that the individual cannot survive with the current environment or the situation is the environment or the situation. So only the strong and intelligent individuals, they can survive, yeah, in to tackle the challenging environment. That is the situation here for the evolutionary process. Right. So yeah, about the GAs, yeah. So as mentioned in the previous slide, there's a GA representing with the binary in this case. So each artificial chromosomes, we can say, consists of the number of genes, and each gene is represented by a binary, yeah, 0 or 1. Yeah. Yeah. So actually, it was concerned with the algorithms that manipulate the strings or binary digits. Yeah, is the algorithm found by John Holland. And nature, yeah, or God's creation, has an ability to adapt and learn without being told what to do. That is, this is actually the biological intelligence. Yeah, the ability to adapt. The biological intelligence of the nature. Yeah, has an ability to adapt. Yeah, and learn. Yeah, without being told, yeah, what to do. Yeah, so that is the nature. Yeah, they have an instinct, or like we can say the sense, yeah, common sense, we can say. And in other words, yeah, the nature finds good chromosomes blindly. Yeah, so then randomly, even blindly. So basically, GAs do the same. Yeah, two mechanism links GA to the problems. Yeah, it is solving, encoding, and evaluation. Yeah, so the GA uses a measure of fitness of individual's chromosome to carry out the reproduction. Yeah, so then the measure of the fitness, yeah, for each individual chromosome. And as reproduction takes place, the crossover operators, yeah, and exchange the part of two single chromosome, for example, and the mutation operator as well, yeah, change the gene value in some randomly chosen location of the chromosome. So these are the operators involved in the GA process. Yeah. So the measure of the fitness, yeah, and reproduction takes place, yeah, with the crossover operator and also the mutation operator. So the genetic algorithm maintains a population of candidate solution for the problem at hand and makes it evolve by iteratively applying a set of stochastic operators. So that is the GA. So actually iteratively applying the set of stochastic operators. So these are the GA stochastic operators. Yeah. First one is selection. Second one is recombination. Yeah. Or crossover, we can say, yeah, mix. And then the mutation. So the selection actually replicates the most successful solution, yeah, found in population, yeah, at a rate proportional to their relative quality. And recombination, we can say crossover here. Actually, the process of decomposing two distinct solutions and then randomly mixes. Yeah, so mix up for both, for example, and the parts, mix up the parts to form the novel solution. So to form the new solution in here. And then mutation actually randomly perturbs, to candidate solution. And this is the metaphor, yeah, with the genetic algorithm and nature or real life. Yeah. So GA with nature or real life. So there is an optimization problem, yeah, and the environment and feasible solution, yeah, for individuals living in that environment. So the individuals should find a feasible solution, yeah, in order to survive. And solutions quality, this relates to the fitness function and individuals' degree of adaptation to its surrounding environment. And in GA, a set of feasible solution and relates to the population of organism or species. And GA stochastic operators, and in nature or real life, actually selection, recombination, and mutation in nature's evolutionary process. And in GA, iteratively applying a set of stochastic operators. And in nature or real life, evolution of population to shift, to shift their environment. So that is GA in real life or nature. And these are some GA application types. Yeah, you can see here the domain of application, yeah, the domain, and this is the application type. So domain of application, yeah, for the control, for example, control domain, yeah, the application type for gas pipeline, oil balancing, missile evasion, pursuit, yeah. So this is the GA application for control. And for design, yeah, can provide semiconductor layout, yeah, aircraft design, keyboard configuration, yeah, and communication networks. Yeah. So these are the application types for design. And for scheduling, yeah. So we use the scheduling, yeah, for manufacturing scheduling, yeah, facility scheduling, resource allocation, yeah, or some others, yeah, even for the lecture or class scheduling. So this scheduling, it relates to the second assignment, yeah, group assignment. So then you can find, but especially for the class scheduling, yeah, any classes. I mean, for school or for university, yeah, or for the exam scheduling or for lecture scheduling, yeah. So yeah, anything that you select, yeah, you choose by yourself, what kind of the problems, and after that you solve, provide the solution. Yeah, for example, you develop the simple user interface, yeah, to provide the scheduling, for example, exam scheduling. Yeah, and then after that, by using the certain parameters you put, then you can generate the scheduling. Yeah, the schedule of the exam. Yeah, for example, and the robotics. Yeah, the domain application can be in robotics. Yeah, so it can be can provide the trajectory planning. Yeah, or path planning. Yeah, here, and also the domain of machine learning. Yeah, can design neural networks, improving the classification and classifier systems. And then the next domain is signal processing. So you can provide the filter design for signal processing, yeah, and game playing, yeah, for poker, checker, prisoner's dilemma, and so on. And combinational optimization. Optimization here can set the covering, traveling salesman, problem routing, pin packing, grab coloring, and partitioning. Right. So these are the some types of application based on the certain domain, from control to combinatorial optimization. Right. So these are the steps of the basic genetic algorithm. Yeah, as we can see here. So there is a 10 step, yeah, for basic GA. So the step 1 represent the problem variable domain as chromosomes of a fixed length. Yeah, so then we have to define this first, yeah, the variable domain as a chromosome of fixed length, and choose size of population and probability of mutation, PM, and crossover, PC. Right, so then we choose these operators, yeah, for population, mutation, and crossover. And second step, yeah, define fitness function. Yeah, so this is important. So we have to give the fitness function in this case, using the certain formula to measure performance of individual chromosomes. Yeah, that is step 2. Yeah, so then define the fitness function. Yeah, actually for the performance measure, yeah, of the individual chromosome. And the third step is randomly generate initial population and chromosomes of size 10. Yeah, that is the one. Yeah. So then in the step 3, yeah, it will randomly generate initial population of size n. And number 4, calculate the fitness of each individual chromosome. Yeah, as we have done before. Yeah, we have the fitness function, and then for each chromosome or for each individual, then we count or calculate the fitness function and the the possibilities, yeah, or the fitness possibilities. Yeah. So then we divide the the probability divided by the summation of the total of the fitness. And then step 5, select a pair of fit chromosomes for mating. Yeah. And step 6, create a pair of offspring chromosomes by applying crossover and mutation. Yeah. And then step 7, place the created offspring chromosomes in the new population. Yeah. And step 8, it will repeat step 5. Yeah. So back to step 5 here. Yeah. Until the size of new population equal to size of initial population n. So then we'll repeat the step 5. Yeah, select a pair of fit chromosomes for mating. Yeah, select a pair of offspring. Yeah, and by applying crossover and mutation. And place the created offspring chromosome in your population. And repeat the 5. Yeah. And then step 9. Replace the initial or the parent chromosomes with the new offspring population. This is the cycle. And we'll replace the initial or parent's chromosome with the new or offspring population. And then step 10, go to step 4. You can see, calculate the fitness of each individual chromosome. Go to the step 4 and repeat the process until the termination criterion satisfied. That is the situation. Yeah, so the step 4 basic genetic algorithm from step 1 to step 10. So another way of looking at this, so it can produce an initial population of individuals for GA and evaluate the fitness of all individuals. And while termination condition or met to, so then we perform the selection of fitter individuals for reproduction here, and then recombine or crossover this one between individuals and mutate the individuals and evaluate the fitness of the modified individuals and generate a new population. And why? So this is another way to look for the genetic algorithm. And this is the simplified flowchart of GA process, genetic algorithm process. So the first one, initial population. This is the initial population. And then get individual fitness. So from the individual fitness, we can construct the selection, and PX, PS selection, PX crossover, and PM is mutation. And after that, based on this selection, crossover, and mutation, can get a new population. From the new population, we check the termination criteria satisfied. If yes, then N. If not, then again cycle to get individual fitness here. Right. So then if not, termination criteria satisfied. If yes, then N. If not, then continue with the get individuals and back again to be proceed to the selection, crossover, mutation, and then we'll generate the new population. All right, so GA process. Here, GA represent an iterative process. Each iteration is called a generation. And a typical number of generation for a simple GA can range from 50 to over 500. The entire set of generation is called a run. So because of GA use a stochastic search, as mentioned before, So the fitness of a population may remain stable for a number of generations before a superior chromosome appears. And a common practice is to terminate the GA after a specified number of generations and then examine the best chromosome in the population. And if no satisfactory solution is found and GA is restarted again, then will be proceed, process at the beginning. Okay. So this is an example, so you can try this one, this maybe you can prepare with papers, you try by your own first. This one example, the case, the problem, sales and profit problem by using the GA. The goal of this was it the sales and profit? The goal is to help the owner of a restaurant find the best combination of possible solution that produces the highest profit. So that is the goal. Of course, if in sales, so then actually the owner want to produce the highest profit by looking for the best combination of the product that they're selling, that they're selling in the restaurant. So find the package, the optimum package actually, in the restaurant. So in order to generate the highest profit. So that is the goal. And then we have to understand the problem. So these are the problems. So decision to make, which is one more profitable. So here, so there are three domain variables. So given the domain variables, price, drink, and speed. In this case, speed of service. So with certain combination, we can provide this domain variables, the price. So the question is, should the price of the burger, because we have a package, a burger and drink, a soft drink in this case. So we have a package, with the price, and then we are looking for the best combination with the highest profit, by this three domain variables. So the price, should the price of the burger be $1 or $2? This one. And should cola or Pepsi be served with the burger? So cola or Pepsi, depends on the, so means that there is a two option, two choices. The first one, $1 or $2, the price of the burger. The second one with the drink, Pepsi, cola or Pepsi, be served. And then the speed of service, should the restaurant provide slow or leisure service by waiter with excess dose or fast? So slow or fast? Snappy service by waiters in white polyester uniform. So slow, leisure, or fast and snappy service. So then there is a two option for all. So you understand this part? From this one, actually, we can understand the situation. Why? Because there is only two options. If we use the binary, they should have two options only. 0 or 1. 0 or 1. 0 means we do not select, 1 we select, for example. So we have to represent all these domain variables with a 0 or 1. Then after that, we construct the combination, the possible combination. How many combination possible? Then we put, for example, only 4 combination. In order to limit the number of the variant, in this case. So There are three decision variables, based on the previous one, based on this one. There are three decision variables, each of which can assume one of two possible values. One of two, because so the option here, price $1 or $2, drink cola or Pepsi, speed slow or fast. So these are the option for each. So based on this, we have two possible values, one or two possible values. Assuming k is the possible value for the decision variable, so k equal to 2, because of k is a possible value, so we can say k equal to, because so only two options over there, two possible values. $1 or $2, cola or Pepsi. And the last one, slow service or fast service. So these are the three possible values with k equal to, because so only two possible values. If there is three possible values, then we put k equal to 3. So assuming L is the length of the string, so then we assume the length of the string of the possible strategy or combination. L we can say 3. So the combination length of the string, we say this is 3. Okay. So the subspace of this problem is 2 power 3. So k power L, so equal to 2 power 3, equal to 8. Actually, there is 8 possible strategies. But in this case, we consider only 4 possible combination. We find only 4 possible combination. For any possible combination. From 8, out of 8. Right? So this is the one. So we represent the problem, the decision to make in a binary. The price, as we have two possible combination, two possible option. So we can say 0 represent $1, $1 at the price. We have a 3 variable here: price, string, and speed. The speed is actually the speed of service. String and speed of service. So price, we have $1 or $2. So if $1, represent 0 represent $1. And then 1 represent $2. Okay. So because we have two options, according to binary, there is only two. Two options here. So 0 and 1. So 0 represent $1, and 1 represent $2. And how about the drink? Because we have two options also in the drink, in a soft drink here. So 0 represent Pepsi, and 1 represent cola. And then speed. How about the speed? Now we have two types of speed or services here, actually. So 0 represent the slow or leisure. So then if you want to provide this combination with the slow service, so then we put 0. If we want to be fast, then put 1. Right? So then 0 represent the slow or leisure, we can say. And 1 represent fast. Right? So based on this combination, as mentioned in this understanding the problem, we have actually 8 possible strategies. But in this case, we take only 4 possible combination, or strategies. We can say strategies. Because a combination of the strategies. Okay, so the strategy 1, for example, we put the price, yeah, $1 and drink with cola and speed fast. Yeah, so then how to represent the binary here? Yeah, can you do this one? Yeah, price $1, right? And then $1 means that what here price $1 what here represent by what 0 or 1?
0.
0, yes, so this is 0. And cola based on drink representation here 1 or 0?
1.
1, yes. And then fast also 1, right? So this is the binary representation with this combination strategy. Yeah, so $1 cola fast and the binary we get 0 1 1, right? And with the second one, this is strategy 1 and strategy 2. Yeah, with the price $1 Pepsi and fast. So we just represent, yeah, based on this one, yeah, representing this combination of this strategy. $1 0, yeah, so this is 0 because of $1 and cola because of cola is 1, yeah, and then fast is 1, right? And then the second strategy combination price $1 means 0, and Pepsi, yeah, Pepsi 0 also, yeah, and then fast 1, and then strategy number 2 and number 3 here. So price $2. So now $2 is 1, right? And then cola is 1. And then leisure, our slow we can based on this is 0. And then strategy number 4, yeah, $1, yeah, is 0, yeah, based on this one. And then cola is 1, and then leisure is 0. Right, so did you understand this one, this part? It's very important, yeah, because this is the first step that when we want to solve the problem by using GA. Yeah, this is the case, sales and profit. Yeah, we can say burger and profit, yeah, or any food. Yeah, but this is the case in the restaurant example. Yeah, because we can easily change this case with the different name. Then after that, you find the solution. Yeah, and yeah, change some values of and also the variable, for example. Yeah, then after that, you find the solution by using GA. Yeah, so then you have to understand the step by step. Yeah, here. Yeah, because if you made the mistake in the first step, then the other step, of course, then will generate the mistakes as well. Yeah, so this is the first one, the important step here. Yeah, so finally, this is 4. Actually, we have based on the K equal to, yeah, the possible value equal to, and L, the length of string 3, then we have 8 actually, possible 8. We can see here, yeah, for example, the combination of 1 1 1, yeah, 3 1, yeah, we don't have. So $2, yeah, let's say, yeah, just to solve, we have actually another 4 strategy, yeah, but we do not put, yeah, we only select 4 here. So we have total 8 strategy. Right? So for example, yeah, here $2, yeah, with the cola, with the fast. So what kind of binary we can get here from $2, cola, and fast? What binary? 111. Yeah, exactly. So 111. Yeah. So then we just continue with this combination, right? Because actually there is 8 possible combination, yeah, or 8 possible strategy. Yeah. So 111, for example, and 100 also not available. Yeah. If we put 100, what will happen here? We can say this is strategy 5. So number 6, for example. So with 100, there is a $2, right? Here $2. The combination will be $2. And then this is what? Soft drink for 100, Pepsi. Yes. And then the surface speed, laser. Yes. Yeah, we can say laser or slow. Yeah. Okay, so then the binary will be 100. Yeah, that's all. So we just continue until finish if we want. Yeah, but in this case, yeah, in this example, we limit the combination until 4. Yeah, 4 possible combination. So you just select any 4 possible combination. Right. So after this step, yeah, we continue the next one. Yeah, the important step, yeah, after representation, yeah, or encoding. Then the fitness function. Yeah, so in this case, we are given the ratio, yeah, fitness ratio. This is the formula of the fitness ratio. Yeah, so the given, yeah, should be given here. Yeah, I mean the fitness ratio. I mean in was it the example or case, yeah, or the problems will be given the fitness ratio, known already. So then you just find, calculate for each. So we have a 4 strategy here. Yeah, 1, 2, 3, 4. Yeah, as you can see here. So with the string, yeah, string xi, this string, yeah. So this strategy, this string, yeah, combination. So strategy 1, yeah, with the 0, 1, 1, and strategy 2, 0, 0, 1, strategy 3, 1, 1, 0, and strategy 4, 1, 0, 1. Yeah. So then we see the fitness. Yeah, we convert to the value, fitness value. Yeah, yeah. With the, if you remember from the first example, so we convert this one to decimal, right? So 011 is 3, right? 3. You remember this one? How to get this number? You understand how to get this number?
Yes, sir.
Okay, good. Yeah. So because of this one is very important. Yeah. This is binary. Yeah. So as I mentioned before, so for example, number 1 here, yeah, I put here number 1. Yeah. So 0, yeah, just to remind. Yeah, 0, 1, 1. So this one, yeah, actually 1 times 2 power, sorry, 0. And this one, 1 times 2 power 1. And this one, 0 times 2 power 2. Yeah. So we'll get the 1, 2, and 0, right? Yeah, so this one, yeah, equal to 3. right? So this is 3. So you can find the others. Yeah. Is it right? This one, 1, 6, and 2. Then you can try, you can check by yourself here. Please check. 0, 0, 1. Is it 1, the result? Because only 1 times 2 power 0. Only 1 times 1. 1, the other 0. So 1. And 1, 1, 0 is 6. Yeah, means that 2 plus 4, right? Because of this is 4, 2, 1 actually. So 0 times 1, yeah, 0, and plus 2 plus 4, so 6. And then this one only 2, yeah, available. The other 0. 0 times 1, 0. 1 times 2, 2, and 0 times 4, 0. So then we have 2 here. All right. So then you check, yeah, you find the total. This all, just summation of this number. 3 times 1, sorry, 3 plus 1 plus 6 plus 2. Right? So 4, 6, and 12. Yeah, this is the total. And the worst means that the lowest, yeah, here, or the, you can say the lowest, yes, worst, yeah, is 1. Yeah. And then the best, 6. Yeah. Yeah. So you get this number, yeah, and after that the fitness ratio, you just enter this x, yeah, the value this x to this formula. Yeah, it's very important formula, right? So for number 3, yeah, the first strategy, yeah, so F3, and this is number 3, this is the value 3 divided by, yes, sigma, yeah, summation, yeah, this one, right? So 12, right? So then equal to, yeah, 1/4, right? So then equal to 0.25. So please check is the others, the other numbers are the right one or not. This is 0.25. So 1/12, is it 0.08? Correct? The fitness
Yes, sir.
ratio. Okay, the second one, second strategy, and the third strategy, yeah, 6/12 is 0.5, yes. And then the fourth, 2/12. Correct, yeah, 0.1666 something, right? So then we rounded this number, yeah, to be 0.17. Okay, so you know this one, huh? So you understand this part, then we continue to the next. Yeah, this is the fitness function. So then based on this, yeah, we create the pie chart here, yeah, here, yeah, for each fitness ratio, yeah, the possibilities, yeah, yeah, the possibilities, yeah, for each. So for example, for number 1 here, yeah, and then this is number 4, and sorry, number 1, number 4. This is number 3, yeah, strategy number 3, and this is 8 is strategy number 2. Right? So this is proportion. Yeah. So 0, 1, 0, strategy number 4, 1, 1, 0, strategy number 3. Yeah. And then 1, 0, 0, 1, strategy number 2, and 0, 1, 1, strategy number 1. So this is the proportion for each. Yeah, so the highest one is number 3, right? And then the lowest one is number 2, yeah, with the 0, 0, 1. Okay. So by the selection or reproduction, yeah. So by using roulette wheel approach, for example, so 110 has possibilities, as we can see here. 110 has possibility 50% or 0.5 to reproduce in the wheel where it has a because so here 180 degree sector, half of the wheel, right, of being selected, this one. So means that strategy 110, strategy number 3, half of the wheel already taken by allocated by 110. So in theoretically, it will be selected 2 times in the next generation. Because of it's half of the this portion, right? So if 2 times selected, then for the next generation, the possibility, because so it is half of the what's it, the circle here, for half of the wheel. And then the second one is 011. 011 is strategy number 1. Is because of 25%. 25% here. This is 50%. So 011, strategy number 1 has possibility 0.25 or 25%, or this is a quarter, 1/4 chances to reproduce. So the same goes to the other string or individual, for the others here. This is number 2, this is number 1, number 2, and number 3, number 4. So we put for each one, in the mating pool, with the reproduction. 1 because of so then we remove the not the selected. This is the selected combination. So means that 001 we do not select 001. So we replace with the 110 with the highest possibility. So then we put 011 selected, 110 selected, because so it can be 2 times. So then we put 2 001 here, and 010 is here, 17%, 17%, this one. So we select only 3, the depends on the possibility. Then we remove 1, since it is very low in terms of the possibility. So then we have a 3 with 1 replace, this 1001 replace with 110 with the highest possibilities here, 110. So then we have the mating pool 011, 110, 110, and 010. With the pool of xi according to this number. Sorry, here fitness. So fitness here, with 3, 6, 011, 3, and then 110, 6, 110, 6, and 010, 2. So then we have a new mating pool selection here for the reproduction. It's 011, 110, 110, and 010. This one before the original one is 001, but it is not selected due to the lowest probability here. So we remove this one and replace with the highest possibility. Then we got this number, right? And after that, you again count the summation, or the total of this. So 9 plus 8, so 17. And then the worst is 2. And then the average, this one, 17 divided by 4. Is it 4.25? 17 divided by 4. Yes, 425. Yeah, 0.1. And the highest one is 6. Yeah, we have a 2.6 here. So understand until this step? You get the point? All right, so then we continue with the crossover, because we have a selection, and then crossover here, and then mutation, and after that the result, all the result. All right, so then from the selection, so fixed point crossover, so 2 parents are chosen based on their fitness, so one, in this case 0, 1, 1, and 1, 1, 0 are selected, here 0, 1, 1 and 1, 1, 0 are selected. This is the original one based on the reproduction or selection. So we bring to the crossover here, and then we select 0, 1, 0, 0, 1, 1 and 1, 1, 0, and randomly select a point between 0 and L minus 1. L minus 1 is the length of the string, which is 3. So 3 minus 1. So suppose the point is 2. 2 in this case. Right. So the parents here, we select 0, 1, 1. And parents, the second one is 1, 1, 0. Right. So we select the point, then after 2, this one is 2, so here, then this is, so then we swap this one, crossover. So from parent 1 to parent 2. So this is the before, this one, this is 0, 1, 1, here, and 1, 1, 0, right? And then we swap. So offspring, the result of the swap here, or the crossover, because of 1 move to the parent 2, here, then we got 1, 0, 1 and 1, 1, 1. Right? So then we will change with crossover point 2, because of this is the length 3, crossover point 2, with the new string here, new string, based on the crossover of the 2 selected parents here, 0, 1, 1 and 1, 1, 0. So then we have a new string with this one, 0, 1, 0 and 1, 1, 1. Right? So then we remove the 2 parents here, the 2 parents here, with the new, after crossover, the new individual after crossover, right? So then we got this one, the fitness, fitness is actually the value, So then this one 0, 1, 0 is 2, and 1, 1, 1 is 7, right? This number, because of 1 plus 2 plus 4, so 7. This is 6, this is same like this. You just bring this one to this. This is new from the crossover process. So you got this result, this table, new table with total, then you total this one, summation, 2 plus 7 plus 6 plus 2, 9 plus 8, so 17. And then the worst, it is 2 here, 0, 1, 0, and average is 17 divided by 4, just total divided by the number of individual. Yeah. So 17 divided by 4. So you get 4.25. Right? Yeah. And the worst is 2, and the best is 7. Yeah, this is the actually the based on the crossover. Yeah, the result of the crossover. Right. So we got this crossover table. Yeah. Then we proceed with the mutation. Yeah. So then you just bring this one. Yeah, the previous table. Yeah, with the represent the change in the gene here. Yeah. And rule to provide guarantee that the search algorithm is not trapped on the local optimum. And parents are chosen randomly. Yeah. Yeah. For example, this one is 0, 1, 0 and 1, 1, 0. Yeah. 0, 1, 0 and 1, 1, 0. Yeah. And then we randomly select a point between 0 and L minus 1. Yeah, L string, the length of the string 3, and suppose the point is 0 and 1. So the parent, yeah, parent 1, yeah, we randomly select 0, 1, 0 and 1, 1, 0. Yeah, this one. Yeah, then we got this one. And then offspring, yeah, because of the mutation. Yeah, so then this one for the what's that, 0 and 1. Yeah, suppose the point is 0 and 1. Yeah, and then this one offspring becoming 1. So 1, 1, 0. Yeah, this one spring, yeah, becoming 1, 0, 1. So 1 becoming 0. Yeah, so 1, 1, 0. Sorry, 1, 0, 0. Yeah, because of 0 replaced by 1 replaced by 0, and this is 0 replaced by 1. Yeah, so this is number 1, and then number 2. Yeah, or 0 and 1. Yeah, yeah. Of the suppose the point is 0 and 1, and then we put this one. Yeah, to is the string xi table. Yeah, and the mutation point, yeah, 0 and 1. Here, 0, 0, 1 and 1, 0, 0. So we put here, and then we got this result. Yeah, yeah, with the actually move from this one. Yeah, this one. Yeah, we select 1, 0, 1 and sorry, 0, 1, 0, and another one is 1, 1, 0. Right. So we select this one and this one. Yeah, this is the highest. We do not select. So then we got the result here. Yeah, yeah. With after we perform the mutation, yeah, with 2 part, yeah, 1, 1, 1, we maintain, and another 1, 0, 1, because we have 2, 1, 0, 1, 0. We have 2, 0, 1, 0, and this is another one. Then these 2 string, yeah, or was that individual replaced with the new, yeah, result from the mutation. Yeah, with the 0, yeah, the point 0 here. Yeah, so 1, 1, 0. Yeah, we put here, and the point 1 here, coming 1, 0, 0. Yeah, yeah. So and then again we count the fitness value. Yeah, the string. Yeah, by using the decimal. So then we get 7. Yeah, 1 plus 2 plus 4, 7. Actually the same like that. Yeah, 7. Because of 1, 1, 1 we do not select. We do not select to be mutated. Yeah, yeah. We select only 0, 1, 0 and 1, 1, 0. And then 1, 1, 0, 6, 1, 0, 0, 4, and 0, 1, 0, 2. Right. So the total we just count here is this one, total 19, 7 plus 6 plus 4 plus 2. And the worst is 2. This is the worst. And the average, yeah. Yeah, we divided the 19 divided by 4. So 4.75. This is average. And then the best one is 7. All right, so these are the result. Yeah, so from the GA, so we have this result, yeah, in total. So then as you can see, yeah, so after starting from the generation 0, yeah, at the beginning, yeah, and then after that we provide the selection. Yeah, this is selection, and this is a crossover. And this is mutation. Oh, sorry. Mutation. Right. So we have this result. Yeah. Well, based on the table, all. Yeah. This is a table 1 from the fitness function here. Yeah. We move this one, the process of the generation 0. And then after that, after selection or reproduction, we use a roll-it wheel approach, and we got this table. Yeah. And then this is crossover. Yeah. For fixed point crossover. Yeah, we got this table. And then this is the mutation. We got this table. And we combine all this table. Right? So then we got this one. So the generation 1 reproduction, this is the selection actually. And then after the crossover, yeah, we got this one. And this is after mutation. We got this one. So the best one is, yeah, the fitness, yeah, the 111 of first year. Yeah, with the average, yeah, 4.75, and the four, total 19. So these are the results, yeah, by using the GA. All right. So did you understand the process? It's very important. Yeah, the step. So then we can get this result until we can get this result. But mostly we use the programming to select this one. If we use only 4, 5, or until 8 individuals, still fine. Yeah, but if we have more, then it'll be complicated, of course, complex. That's why we just select, for example, yeah, we put, okay, the limitation, okay, take 4 individuals, even though we have 8 possibilities, because of A, yeah, the option is 0 and 1. So we have 2 options. And also the length, we have 3 string for the length. It's 111 or 011 or 101. If for length, then for the length 4, then we have different, yeah, because this is 2 option. Yeah, so K equal to 2 and L equal to 3. Yeah, for the string of the XXX, yeah, in binary, right? If we have 4, then XXXX or AAA, for example. 3 binary. Yeah. So then the length will be 4. And if the length is 4, then the possibility of the combination will be, yeah, 2 over 4. Right? Yeah. So yeah, the possibility is, yeah, 16. Yeah? So if 2 power 3 is this one, we have a 2 power 3. So we have 8. And this one we have 16. So 16 possible combination, yeah, for this was the problem, yeah, to solve the problem.